Right now, at this very second, the Large Hadron Collider is pushing protons to 99.9999991% the speed of light. They have poured enough energy into each proton to equal 7,000 times its own resting mass. And still, not a single one of those particles has reached light speed, not because engineers ran out of power, because the universe itself restructures how energy, time, and motion relate to each other as anything approaches that boundary. What you are about to discover is not a story about going fast. It is a story about what happens to reality when motion reaches the threshold, where cause and effect begin to unravel. This is the most disturbing speed limit in physics, and the fine you pay for breaking it is not a ticket. It is the collapse of chronological order. If you enjoy documentaries that make you rethink how reality actually works, do me a favor and hit that like button and subscribe. It genuinely helps this channel keep making these deep dives. And before we begin, we're now live on Spotify. The link's in the description if you'd like to listen wherever you are. Now, settle in and get yourself comfortable. Let's begin. You already know the number, 186,282 miles per second, 670 million miles per hour, the speed of light in a vacuum. You have heard it repeated in classrooms, documentaries, and science fiction since you were old enough to wonder what sits at the edge of the universe. It is the most famous speed limit in nature, and nearly everything you assume about it is wrong. Most people imagine the speed of light the way they imagine any other speed. A very large number on a cosmic speedometer, the fastest thing going, the record holder. And like any record, the assumption is that it can be beaten, or at least matched, with enough energy, enough ingenuity, enough determination. You picture a spacecraft accelerating harder and harder until the needle finally reaches that legendary number, and then maybe, just maybe, pushing past it. That picture feels intuitive, it feels logical, and it is completely misleading, because the speed of light is not a speed in the way you have ever experienced speed before. It is a structural boundary woven into the geometry of the universe, and what happens as you approach it has nothing to do with going fast and everything to do with reality quietly rearranging itself around you. To understand why this matters, we need to start with something that seems unrelated: time. Your sense of time right now as you listen to this feels absolute. 1 second for you is 1 second for everyone. The clock on your wall ticks at the same rate as the clock on the International Space Station, the clock in a laboratory in Geneva, the clock on a satellite orbiting 20,000 kilometers above your head. That feeling of universal time, of one shared now ticking away at the same pace for everything in the cosmos, is one of the most deeply held assumptions in human experience. And it is false. In 1905, Albert Einstein published a paper that quietly demolished universal time. The paper introduced what we now call special relativity, and its central premise was deceptively simple. The laws of physics are the same for all observers who are not accelerating, and the speed of light in a vacuum is the same for all such observers regardless of how they are moving. That second statement sounds harmless. Light moves at a fixed speed. Fine, but the consequences are shattering. If the speed of light is truly the same for everyone, then something else has to give when two observers are moving relative to each other. What gives is time itself. Moving clocks tick slower than stationary ones, not because the clock is broken, not because the mechanism is failing, because time itself passes at a different rate for the moving object. The faster you move relative to someone else, the more your clock falls behind theirs. This is not a thought experiment. This is not a metaphor. This is measured, confirmed, engineered around physical reality. In 1971, a physicist named Ha-Fu and an astronomer named Keating packed 4 cesium atomic clocks onto commercial airline seats. The clocks had their own tickets. They flew those clocks around the world twice, once heading east and once heading west, then compared them to identical clocks that stayed behind at the United States Naval Observatory in Washington. The clocks disagreed. The eastbound clocks, which were moving faster relative to Earth's surface because they travelled in the direction of the planet's rotation, lost 59 nanoseconds compared to the ground clocks. The westbound clocks, moving slower relative to the surface, gained 273 nanoseconds. These differences match the predictions of special and general relativity almost exactly. Time was not universal. It depended on motion. 59 nanoseconds sounds trivial. It sounds like a rounding error, a curiosity too small to matter. But that is only because commercial aircraft move at a tiny fraction of the speed of light. Scale the velocity upward, and the effect explodes. At 10% of the speed of light, a moving clock loses roughly 0.5% of its time compared to a stationary one. At 90% of light speed, a moving clock ticks at less than half the rate of a stationary clock. At 99%, the moving clock runs at barely 1/7 the stationary rate. And as you push closer and closer to 100% toward the actual speed of light, the moving clock approaches a full stop. Time dilation is not a gentle curve. It is an exponential escalation that grows more dramatic the faster you move, and it races toward infinity as you approach light speed. This is not theoretical. This is measured every single day inside the most precise engineering system humanity has ever built. The Global Positioning System, GPS, depends on a network of satellites orbiting approximately 20,000 kilometers above Earth at speeds of roughly 14,000 kilometers per hour. That is fast by human standards, but it is a vanishingly small fraction of light speed. Even so, the relativistic effects are large enough to destroy the system if they are not corrected. Here is what happens. Special relativity predicts that the satellite clocks, because they are moving relative to clocks on the ground, should fall behind by about 7 microseconds per day. General relativity, Einstein's broader theory that includes gravity, predicts that because the satellites experience weaker gravity than the surface, their clocks should run faster by about 45 microseconds per day. The net effect is that satellite clocks gain approximately 38 microseconds per day compared to ground clocks. 38 microseconds. That is 38 millionths of a second. But GPS requires nanosecond precision to calculate your position accurately. If engineers ignored relativity, your position reading would drift by roughly 10 kilometers every single day. Within a week, the entire GPS network would be useless. So engineers build the correction directly into the hardware. Before a GPS satellite is launched, its onboard atomic clock is deliberately set to tick at a slightly lower frequency than the intended operational rate. Specifically, the clock is tuned to approximately 10.229999999543 MHz on the ground, so that once it reaches orbit and relativistic effects speed it up, it arrives at the target frequency of 10.23 MHz. This is not optional. This is not a safety margin. Without this adjustment, modern navigation collapses. Every time your phone tells you where you are, it is performing a calculation that only works because Einstein was right about time. But the GPS correction handles the steady, predictable part of the relativistic shift. Satellite orbits are not perfectly circular. As the satellite moves through slightly higher and lower altitudes and slightly faster and slower speeds within its orbit, additional small relativistic wobbles appear. These are corrected by calculations performed inside your GPS receiver itself, in real time, continuously adjusting for the fact that time does not pass at the same rate everywhere in the solar system. You carry a relativity calculator in your pocket. You use it to find the nearest coffee shop. Now here is where the story takes its first unsettling turn. Time dilation is not confined to clocks on airplanes and satellites. It applies to everything. Biological processes, chemical reactions, the firing of neurons in your brain. If you were traveling at 90% of the speed of light, your heart would beat at less than half the rate experienced by someone watching you from the ground. You would age at less than half the pace. A journey that takes 10 years by your onboard clock might correspond to 23 years passing for everyone you left behind. This is not an illusion. You would genuinely experience less time. You would arrive younger than you should be, with fewer heartbeats behind you, fewer breaths drawn, fewer thoughts completed. The universe does not merely appear to change when you move fast. It actually changes. Time itself becomes relative. Nature confirms this constantly, not with satellites and airplanes, but with subatomic particles. Muons are unstable particles produced when cosmic rays from deep space slam into the upper atmosphere. They have a measured half-life of about 2.2 microseconds when they are stationary in a laboratory, At that decay rate, even traveling near light speed, muons produced at altitudes of 15 kilometers should disintegrate long before reaching the surface. They should not survive the trip. Yet ground-based detectors observe muons arriving in enormous numbers. The explanation is time dilation. Muons produced by cosmic ray collisions travel at approximately 99.9% of light speed. At that velocity, their internal clocks slow so dramatically that their brief lifetime stretches by a factor of roughly 22 relative to an observer on the ground. 2.2 microseconds in the muon's frame becomes nearly 50 microseconds in ours. That is enough time to reach the surface before they decay. The muons do not know they are living longer. From their own perspective, they exist for exactly 2.2 microseconds, but the distance they need to cross appears contracted from their frame of reference. Length contraction, the spatial counterpart to time dilation, squeezes the 15-kilometer atmospheric column into something much shorter from the muon's perspective. Both effects, time dilation and length contraction, are two faces of the same underlying reality. Space and time are not separate. They are woven together into a four-dimensional fabric called space-time, and motion through that fabric changes how you experience both dimensions. This brings us to the deeper question. Why does the speed of light appear in these equations at all? Muons are not made of light. Airplanes are not made of light. GPS satellites have nothing to do with photons. So why does the speed of light dictate how time and space behave for massive objects? The answer is that the speed of light is not fundamentally about light. It is about the structure of space-time itself. Light happens to travel at this speed because photons are massless, and massless particles always travel at the speed built into the geometry of the universe. But even if light did not exist, even if photons were never part of the story, the speed would still be there. It would still appear in E equals mc squared. It would still govern time dilation. It would still set the maximum rate at which any cause can produce an effect anywhere in the cosmos. Physicists sometimes call it the speed of causality rather than the speed of light, and that name reveals something critical. This speed is not a property of a particular particle, it is a property of the universe itself. James Clerk Maxwell discovered a clue to this truth in the 1860s, long before Einstein was born. Maxwell unified electricity and magnetism into a single theoretical framework and found that the equations predicted electromagnetic waves that would propagate at a specific speed. That speed, calculated purely from the electric and magnetic constants of free space, turned out to be the measured speed of light. Light was an electromagnetic wave, and its speed was baked into the fundamental constants of electromagnetism. It was not a coincidence. It was a structural feature of reality. Later, Einstein's special relativity revealed that this same speed governs the transformation between different reference frames. The Lorentz transformations, the mathematical rules describing how measurements of space and time change between observers moving relative to each other, contain this speed as their central parameter. Every equation that describes how motion alters measurement includes it. The speed of light is the conversion factor between space and time. It tells you how much distance is equivalent to how much duration. It is the exchange rate between meters and seconds in the geometry of the cosmos. This is why the number keeps appearing in places that seem to have nothing to do with light. E equals mc squared does not describe photons. It describes the relationship between mass and energy for everything. The c in that equation is not there because light is involved. It is there because the equation is written in the language of space-time, and c is the fundamental constant of space-time geometry. Every particle, every force, every interaction obeys this geometry. There is no way to escape it without breaking the framework that makes physics self-consistent. The Lorentz factor is the mathematical expression that captures how dramatically reality changes as you approach this speed. Physicists write it as gamma equals 1 divided by the square root of 1 minus v squared over c squared. At low speeds, when v is tiny compared to c, gamma is almost exactly 1. Nothing unusual happens. Time passes normally, lengths stay the same, energy behaves classically. But as v approaches c, the denominator shrinks towards 0, and gamma begins climbing. At 50% of light speed, gamma is about 1.15, noticeable, but modest. At 90%, gamma reaches approximately 2.3. Time for the moving object passes at less than half the rate for a stationary observer. At 99%, gamma is about 7.1. At 99.9%, gamma is approximately 22.4. At 99.9999991%, the speed of protons in the Large Hadron Collider, gamma reaches approximately 6,927. That last number deserves a pause. A proton in the Large Hadron Collider at full energy has a Lorentz factor of nearly 7,000. This means that 1 second of time for that proton corresponds to nearly 2 hours for the scientists in the control room. It means the proton's kinetic energy is nearly 7,000 times its own rest mass energy. It means that despite carrying almost 7 tera-electron-volts of energy, the proton is still traveling below the speed of light, not by much. It is moving at 99.99991% of light speed. The gap between that velocity and light speed is almost unimaginably small, yet that tiny gap is absolute. No amount of energy will close it. In 2026, a study analyzing ultra-high energy gamma rays from distant cosmic events tested whether light speed varies with photon energy. The researchers found no dependence whatsoever. The speed of light is constant across every energy scale tested, reinforcing the Lorentz invariance that underpins all of modern physics. The cosmic speed limit is not approximate. It is exact. It is structural, and it has been tested to precision that would have seemed like sorcery a century ago. This brings us to length contraction, the spatial twin of time dilation. As an object moves faster, it physically shortens along the direction of motion as measured by a stationary observer. At 50% of light speed, an object contracts to about 87% of its resting length. At 90%, it shrinks to about 44%. At 99.99%, it compresses to less than 1.5% of its original length. A spacecraft 100 meters long traveling at this speed would measure less than 1.5 meters from nose to tail as seen by someone it flies past. This contraction is not an optical illusion. It is not the result of light signals arriving at different times from different parts of the object. It is a genuine change in the measured spatial dimension of the object from the perspective of the observer's reference frame. The object itself, in its own frame, feels no compression. Its occupants measure it at its normal length, but the stationary world sees it flattened. And the object, in turn, sees the stationary world flattened. Each frame of reference is equally valid. Neither is wrong. Neither is an illusion. Both are correct measurements of a reality that depends on the relative motion of the measurer. This symmetry between observers is one of the most counterintuitive features of special relativity. You might expect one perspective to be the true one and the other to be distorted, but relativity insists there is no privileged frame, no absolute rest, no universal clock keeping the real time while everyone else's clocks run wrong. Every inertial frame of reference has equal claim to being correct. The differences in measured time and length are not errors. They are features of the space-time geometry itself. Hermann Minkowski, Einstein's former mathematics professor, recognized this in 1908 when he reformulated special relativity in geometric terms. He showed that space and time are not separate entities, but components of a unified four-dimensional manifold. Events do not happen at a location in space and a moment in time. They happen at a point in space-time. The distance between two events in this four-dimensional framework is not measured in meters or seconds alone, but in a combined quantity called the space-time interval. And this interval is the same for all observers, regardless of their motion. It is invariant. The space-time interval is calculated using a formula that includes the speed of light as the conversion factor between spatial and temporal components. When you move through space, you trade some of your motion through time for motion through the spatial dimensions. The faster you travel through space, the slower you move through time. This is not a metaphor. It is the geometry. At rest, you move entirely through time and not at all through space. At the speed of light, you would move entirely through space and not at all through time. Everything in between is a blend, a rotation in four-dimensional spacetime that shifts the balance between your spatial and temporal velocity. This geometric picture explains why the speed of light is a boundary rather than a number. It is not that the universe prohibits going faster. It is that the mathematical structure of space-time does not have room for a massive object to reach that speed. As your spatial velocity increases, your temporal velocity decreases. To reach the speed of light, your progress through time would have to reach zero. For a massive particle, this requires infinite energy, which is impossible. The speed of light is not a wall you hit, it is an asymptote you approach, a limit that the equations curve toward but never touch. Every unit of energy you add gets you fractionally closer, but the remaining gap never fully closes. This is what makes the speed of light fundamentally different from every other speed in nature. The sound barrier was an engineering challenge. Engineers built aircraft strong enough and powerful enough to push through the pressure wave that builds at the speed of sound, and once they crossed it, physics continued normally on the other side. The speed of light has no other side. There is no regime beyond it where physics resumes its familiar behavior. The mathematics does not continue past the boundary. It breaks. The Lorentz factor becomes imaginary. Measured quantities lose their physical meaning. The equations that describe how energy, time, and space relate to each other stop returning answers that correspond to anything in observable reality. And here is what should genuinely disturb you. This is not just mathematics. The 2026 gamma-ray study, the GPS corrections, the muon survival rates, the Haarfurler and Keating clocks, the protons in the Large Hadron Collider, every piece of experimental evidence confirms that reality actually works this way. Time actually dilates, length actually contracts, energy actually climbs toward infinity as mass approaches light speed. These are not theoretical predictions awaiting future confirmation. They are confirmed facts, tested to extraordinary precision across decades of increasingly sensitive experiments. The universe genuinely changes its behavior as velocity increases, time slows, space compresses, energy demands rise without limit. You are not approaching a speed limit. You are approaching a transformation, a regime change in how the universe processes motion, time, and energy. And you have not even crossed the boundary yet. Everything described so far happens below the speed of light. Every experiment, every measurement, every confirmed observation occurs in the sublight regime, where reality, although distorted, remains self-consistent. Clocks disagree about how much time has passed, but they still tick forward. Lengths change depending on who measures them, but they remain positive. Energy grows enormous, but it remains finite as long as you remain below the limit. The question nobody can answer with a simple experiment is what happens if you cross it, not approach it, not asymptotically curve toward it, actually cross it, move from below light speed to above it. That question is not merely harder than the approach, it is qualitatively different. Because everything the universe does as you approach the boundary, the time dilation, the length contraction, the runaway energy cost, all of it points in one direction. It points toward a threshold that cannot be crossed by any continuous acceleration of a massive object. And the mathematics suggests that what lies beyond is not simply faster travel, it is something far stranger, something that does not look like motion at all. What comes next will show you exactly what the universe does when you try to force it past this threshold, and why the energy cost is not even the most disturbing part of the story. There is a lie hidden inside the way we talk about particle accelerators. We say they accelerate particles. The name itself tells you what they supposedly do. They take something slow and make it fast. And in the early days, that description was accurate. The first cyclotrons in the 1930s took protons sitting nearly at rest and pushed them to a few percent of the speed of light. Real acceleration, measurable increase in velocity. But the machines we operate today do something profoundly different. And the difference reveals one of the deepest truths about the light speed boundary. The Large Hadron Collider near Geneva is the most powerful accelerator ever constructed. Its underground ring stretches 27 kilometers in circumference. Superconducting magnets cooled to 1.9 degrees above absolute zero bend proton beams. Around that ring at energies reaching 6.5 tera-electron volts per beam. The energy investment is staggering. The electrical power consumed by the facility could service a small city. And the result of all this effort, all this infrastructure, all this expense, is a speed increase over the previous generation of accelerators that you would need scientific notation to express as a decimal. Here is the critical detail. When protons enter the Large Hadron Collider's main ring, they are already traveling at 99.9998% of the speed of light. They arrive from a chain of smaller pre-accelerator stages that have already spent enormous energy getting them to that velocity. The 27-kilometer ring then pours in thousands of times more energy, and the final speed is 99.999991% of the speed of light. The entire Large Hadron Collider, the most powerful particle accelerator in human history, the product of decades of international collaboration and billions of dollars, closes a speed gap of less than 0.2 of a percentage point. Hear that again. The gap between the entry speed and the exit speed is so small, no ordinary instrument could distinguish them. Yet the energy required to close that gap is monstrous. This is not a failure of engineering. This is physics telling you something fundamental about the nature of the boundary you are approaching. The relationship between energy and speed is not linear in the relativistic regime. It is not even polynomial. It is asymptotic. The speed of light sits at the top of a curve that rises toward infinity. Every additional increment of speed, every fractional step closer to the limit, demands exponentially more energy than the last. At low velocities, doubling your energy roughly doubles your speed. Near light speed, doubling your energy barely changes your velocity at all. The energy pours in and the speedometer barely moves. So where does all that energy go? It goes into something that has no equivalent in ordinary human experience. At relativistic velocities, the energy you pump into an object stops converting efficiently into speed and begins converting into what physicists describe as relativistic momentum and kinetic energy that manifests as increased inertia. The object does not get faster in any meaningful sense. It gets heavier. Not heavier in the way that a truck is heavier than a bicycle. Heavier in the sense that it resists acceleration more and more for every unit of force applied. The property that determines how hard something is to push, its inertia, grows without limit as the object approaches light speed. Classical momentum is simple. It equals mass times velocity. Double the velocity and you double the momentum. But relativistic momentum is mass times velocity times the Lorentz factor gamma. And gamma, as we established, climbs toward infinity as velocity approaches the speed of light. At 90% of light speed, gamma is about 2.3, so the momentum is 2.3 times what you would expect classically. At 99%, gamma is about 7.1. At 99.9%, gamma reaches roughly 22. At the velocities achieved in the Large Hadron Collider, gamma exceeds 6,900. The proton's momentum is nearly 7,000 times larger than classical physics would predict for a particle moving at nearly the same speed. All that excess momentum comes from the energy that was supposed to make the proton faster, but instead made it more resistant to further acceleration. Think of it this way. Imagine you are pushing a sled across a frozen lake. At first, every push adds noticeable speed. The sled glides faster and faster. But now imagine that with every push, the sled itself grows heavier. Not a little heavier, dramatically heavier. By the time you have been pushing for a while, the sled weighs as much as a car, then a building, then a mountain. You are still pushing with enormous force, and the sled is still on smooth ice, but it barely moves faster because its resistance to your push has grown to match and exceed anything you can supply. That is what happens to a particle approaching light speed. The ice never runs out, the friction never increases, but the sled becomes the planet. Particle physics history is essentially the story of humanity learning this lesson the hard way through increasingly expensive machinery. In the 1950s, the cosmotron at Brookhaven could accelerate protons to roughly 97.5% of the speed of light. Impressive for the era. The alternating gradient synchrotron, commissioned at the same laboratory in 1960, pushed protons to 99.96%, a massive leap in energy, yet the speed gain over the cosmotron was barely 2.5 percentage points. By the time Fermilab's Tevatron came online in 1983, protons reached 99.9995% of light speed. The energy had increased by orders of magnitude compared to Brookhaven, but the speed gain had collapsed to a few hundredths of a percent. The Large Hadron Collider, operating at roughly 7 times the tevatron's energy, nudged the speed by another almost invisible fraction. One experiment demonstrated this reality with exceptional clarity decades before the Large Hadron Collider existed. In the early 1960s, physicists at the Stanford Linear Accelerator Center, known as SLAC, built a 2-mile-long straight-line accelerator designed to push electrons to extreme energies. Electrons are nearly 2,000 times lighter than protons, which means relativistic effects become dramatic at much lower energies. The SLAC machine could pour enormous energy into these lightweight particles and then directly measure their resulting velocities. What the researchers observed became one of the most elegant confirmations of special relativity ever recorded. At low energies, the electrons responded as Newton would have predicted. More energy produced proportionally more speed. The relationship was clean and linear. But as the electrons approached the speed of light, the curve bent. Energy kept climbing, but velocity began to plateau. The experimenters doubled the energy input. The speed barely changed. They doubled it again. The speed changed even less. They pushed the electrons to energies thousands of times greater than the particle's resting mass. The velocity was pinned just below light speed, refusing to close the final gap no matter how much energy was added. The data, when plotted on a graph, traced an unmistakable asymptotic curve. Speed rose steeply from zero, bent smoothly through the mid-range, and then flattened into a nearly horizontal line, kissing the speed of light from below. The curve matched the predictions of special relativity with extraordinary precision. There was no ambiguity, no competing interpretation. The electrons were not being slowed by friction, by air resistance, by any external force. They were encountering the geometry of space-time itself. The energy was going somewhere real, into relativistic momentum and kinetic energy, but it was not going into speed. SLAC showed, in one continuous measurement, the exact mathematical shape of the wall. The universe was drawing it on a graph for anyone willing to look. Each generation of accelerator costs more, consumes more power, requires more sophisticated engineering, and produces a smaller increment of speed than the one before. If you plotted the speed achieved by every major accelerator in history on a graph, you would see a curve that rises steeply at first and then flattens into a nearly horizontal line, just below 100% of light speed. The curve never touches the ceiling. No matter how far you extend the horizontal axis into the future, no matter how much energy you imagine pouring in, the line approaches but never meets the limit. That is what an asymptote looks like. And that asymptote is not an engineering obstacle. It is the shape of space-time. A question that often arises at this point is simple and fair. If you cannot reach the speed of light, how close can you actually get? And the answer is as close as your energy budget allows. There is no second wall before the main one, no intermediate barrier. At 99.999%, where physics changes again, the asymptote is smooth and continuous. You can always get closer with more energy. At the Large Hadron Collider, protons reach a Lorentz factor of roughly 7,000. A hypothetical accelerator 1,000 times more powerful might push the Lorentz factor to 7 million. The speed would increase from 99.9999991% to 99.99999999% of light speed. An unimaginably small speed gain for an unimaginably large energy investment. The returns diminish without ever reaching zero. You can always buy one more decimal place. You can never buy the last one. Now apply this to something more personal than protons. Imagine a spacecraft, a real vessel attempting to reach a significant fraction of light speed for interstellar travel. The energy requirements become terrifying almost immediately, even for an object you could hold in your hand. A typical modern spacecraft, like the ones used to send probes to the outer solar system, travels at roughly 17 kilometers per second relative to the Sun. That is about 0.0057% of light speed. Fast by everyday standards, functionally stationary by relativistic standards. To accelerate a single kilogram, roughly the mass of a textbook, to just 10% of light speed would require approximately 4.5 times 10 to the 14th joules of kinetic energy. That is roughly equivalent to the energy released by 100,000 tons of TNT for 1 kilogram at 10%, a speed at which relativistic effects are barely noticeable. To reach 50% of light speed, the energy requirement does not merely double or triple. It jumps to approximately 1.4 times 10 to the 16th joules. To reach 90%, it climbs to approximately 1.2 times 10 to the 17th joules, and to reach 99%, it soars to approximately 5.5 times 10 to the 17th joules. Each step closer to the limit demands a multiplicative increase in energy that outpaces any linear or even quadratic scaling. By the time you are discussing 99.9%, the energy for that single kilogram exceeds the total annual energy consumption of entire nations. And here is the part that makes the problem qualitatively different from any engineering challenge humanity has faced. The energy does not just need to be generated, it needs to be carried. A rocket works by expelling mass out the back. The fuel is part of the payload until it is burned. If your fuel weighs more than your payload, you need more fuel to carry the fuel, which means you need more fuel to carry that fuel, and the calculation spirals into what rocket engineers call the tyranny of the rocket equation. For chemical rockets, this tyranny already makes interstellar travel impractical. For relativistic speeds, even if you imagine a perfectly efficient engine that converts mass directly into energy, using the full E equals mc squared conversion, the fuel requirements grow exponentially with the desired Lorentz factor. To reach a gamma of 7, which corresponds to roughly 99% of light speed, the mass of fuel consumed would need to exceed the mass of the payload by a factor of roughly 13 to 1, even in the theoretical best case. To reach a gamma of 100, the ratio exceeds 200 to 1. To match the Large Hadron Collider's proton gamma of 7,000, you would need a fuel-to-payload ratio exceeding 14,000 to 1 for a single trip, and any attempt at a round trip would compound that ratio to the point where the fuel mass dwarfs the payload by factors measured in the quadrillions. This is why faster-than-light travel cannot be understood as an extension of the engineering problem of fast travel. The energy barrier is not a wall you could theoretically scale with better technology. It is a curve that rises toward infinity. No finite energy source, no matter how advanced, can produce infinite energy. The barrier is not practical. It is mathematical. But the energy story is only half the picture. The other half is what happens to time, and this is where the human consequences become genuinely disorienting. The twin paradox is the most famous illustration. It is often presented as a puzzle or a riddle, but it is neither. It is a confirmed prediction of special relativity with no actual paradox once the physics is understood. Here is how it works. Two identical twins live on Earth. One stays home, the other boards a spacecraft that accelerates to a large fraction of light speed, travels to a distant star, decelerates, turns around, and returns home. When the travelling twin arrives back on Earth, less time has passed for her than for her sibling. She is younger. Not because her clock malfunctioned, not because her perception was altered, because fewer seconds, fewer heartbeats, fewer chemical reactions, fewer everything actually occurred for her during the journey. Time itself was shorter for the moving twin. The amount of the discrepancy depends on speed and distance. Consider a concrete scenario. A spacecraft accelerates to 90% of light speed and travels to a star 4.2 light-years away, roughly the distance to Proxima Centauri. At 90% of light speed, the journey takes about 4.7 years as measured by observers on Earth. But the travelling twin, experiencing time dilation with a Lorentz factor of approximately 2.3, ages only about 2 years during the outbound leg. The same occurs on the return trip. By the time she lands back on Earth, roughly 9.4 years have passed at home, but she has aged only about 4 years. She returns to find her twin more than 5 years older than she is. Scale the speed upward, and the disparity becomes grotesque. At 99% of light speed, the Lorentz factor is approximately 7.1. A round trip to a star, 50 light-years away, takes roughly 100 years on Earth, but only about 14 years for the traveller. She returns to a world where everyone she knew is dead. Her grandchildren might be elderly. At 99.9%, The Lorentz factor reaches roughly 22.4. The same 50 light-year round trip still takes about 100 years on Earth, but the traveller experiences fewer than 5 years. She steps off her spacecraft into a century she never lived through, and at 99.99%, gamma exceeds 70. Trips spanning hundreds of light-years compress into single years of shipboard time, while millennia pass on Earth. The traveller becomes a time traveller, not in the science fiction sense of jumping to a specific date, but in the far more disturbing sense of being permanently displaced from her own era. She can never go back to the time she left. She arrives in the future with no return ticket. And the displacement does not stop at centuries or millennia. Push the velocity higher, and the temporal gulf widens into something no longer measured in human terms. At a gamma of 10,000, a one-year shipboard journey corresponds to 10,000 years on Earth. The traveller who departs today returns to find that every language she spoke has been dead for millennia. Every city she knew has been buried, excavated, studied, and forgotten. The continents have not yet moved appreciably at that timescale, but human civilization is unrecognizable, if it exists at all. She is not returning to a different era. She is returning to a different world. At a gamma of 100,000, the displacement reaches geological time. One shipboard year equals 100,000 Earth years. Ice ages have come and gone. Coastlines have shifted. Species have evolved and vanished. Pushed to a gamma of 1 million, and the displacement enters the realm of stellar evolution. Nearby stars have moved. Some have died. New ones have ignited. The constellations are gone, replaced by unfamiliar patterns that no human eye ever named. At the most extreme gammas theoretically achievable, the displacement reaches cosmological scales. A traveller at sufficient velocity could experience a single decade of personal time while billions of years pass for the rest of the universe. She would return, if return were even possible, to a cosmos in which the sun has exhausted its fuel and swollen into a red giant, consuming Mercury, Venus, and possibly Earth. The solar system she launched from no longer exists in any recognizable form. The galaxy itself has changed, merged with Andromeda, settled into a new elliptical structure populated by aging red stars. She left a vibrant spiral galaxy and returned to a galactic graveyard, not because she travelled far, because she travelled fast. The speed did not carry her across distance, it carried her across time. And at the extreme end of the curve, the time it carries you across is not human time, it is cosmic time. The lifetime of stars, the evolution of galaxies, the aging of the universe itself, this is the final, most unsettling truth about approaching the speed of light. It does not merely separate you from your own era, it separates you from your own universe. Not spatially, temporally. The cosmos you left continues without you, aging at its normal rate while your clock nearly stops, and there is no way to reverse it. There is no mechanism to reclaim the time the universe spent while you were frozen in relativistic transit. The displacement is permanent, cumulative, and proportional to how close you pushed against the boundary. The speed of light does not just resist being reached. It punishes the attempt with exile. Not exile from a place, exile from a time. This is not fiction. This is what the equations demand, and every experiment that tests the underlying physics confirms they are correct. The clocks do not lie. The muons do not lie. The GPS satellites do not lie. The protons in the accelerator do not lie. If you move fast enough, you genuinely age less than the people you leave behind. The universe does not owe you a shared timeline. There is no mechanism by which you can maintain synchrony with Earth while travelling at relativistic speed. The act of moving near light speed fundamentally decouples you from the temporal context of your origin. And this decoupling is not symmetric in the way you might expect. While the travelling twin is in motion at constant velocity, she can justifiably claim that Earth is moving relative to her. From her frame, Earth's clocks should run slow. This is the apparent paradox. Each twin thinks the other's clock is slow, but the resolution is precise and well understood. The travelling twin must accelerate, decelerate, turn around, and accelerate again to return home. These changes in velocity break the symmetry between the two frames. The travelling twin occupies at least two distinct inertial frames during her journey. one outbound and one returning, while the stay-at-home twin occupies a single inertial frame throughout. General relativity and the proper time calculation confirm without ambiguity that the traveller ages less. The resolution is not debated among physicists. It is settled. This has a consequence that rarely appears in popular science discussions, but matters enormously for understanding what light speed really is. The closer you travel to the speed of light, the more your subjective experience of the journey compresses. At 99.9999% of light speed, the gamma factor exceeds 700. A trip to a star 700 light-years away, which takes just over 700 years from Earth's perspective, takes only 1 year of shipboard time. In principle, a traveller at extreme velocities could cross the entire observable universe within a single human lifetime, as measured by her onboard clock. The distance is not shortened in any absolute sense. The universe is still billions of light-years across, but her personal time is so dilated relative to the external universe that what takes billions of years out there takes only decades for her. This creates one of the most haunting asymmetries in physics. You could, in principle, reach the edge of the observable universe before you die, but everyone and everything you left behind would be long gone, separated from you not by distance but by time. Your journey compresses your personal clock. It does not compress the universe's clock. When you arrive, cosmic ages have passed. Civilizations have risen and fallen. Stars have been born and burned out. You did not travel to a distant place. You traveled to a distant time. And the faster you went, the more extreme the displacement. But temporal displacement is not the only thing that changes for the relativistic traveller. The universe itself looks different from inside a vessel moving at extreme velocity. At speeds above roughly 87% of light speed, a phenomenon called relativistic aberration begins reshaping the sky. Light from stars that should appear beside or even behind the spacecraft gets compressed into a narrowing cone ahead of it. The faster you travel, the tighter the cone becomes. At 99% of light speed, nearly the entire sky collapses into a brilliant disk concentrated in front of the vessel. Stars that were overhead, to the sides, and even behind you all appear to migrate forward, their light bent by your motion into a single blazing region directly ahead. Simultaneously, relativistic Doppler effects transform the colours of everything you see. Stars ahead of you are blue-shifted, their light compressed to shorter wavelengths. What was visible orange starlight becomes ultraviolet, then X-ray radiation. Stars behind you are red-shifted into invisibility, their light stretched to wavelengths far beyond what human eyes or even most instruments can detect. The cosmic microwave background radiation, normally an invisible whisper of microwave photons left over from the earliest era of the universe, blue shifts into the visible spectrum ahead of you. At extreme gamma, it shifts further into ultraviolet and then into X-ray territory, bombarding the front of the vessel with radiation that was never meant to be seen. The traveller at extreme relativistic speed does not experience a faster version of normal space travel. She experiences a fundamentally alien sensory environment. The sky is not a dome of scattered stars. It is a blinding searchlight ahead and absolute blackness behind. The familiar constellations do not merely change position. They cease to exist as recognizable patterns, crowded together into a single, overwhelming concentration of light. Navigation by starlight becomes impossible. The traveller is not just displaced in time. She is sensorially severed from the universe she is crossing. The cosmos outside her window bears no resemblance to the cosmos she left behind. Even light itself, the one constant in the equations, arrives in forms she was never evolved to perceive. This is not a minor detail of the relativistic experience. It is a direct physical consequence of the Lorentz transformations applied to incoming light. The same equations that predict time dilation and length contraction also predict this visual transformation, and it gets more extreme without limit as velocity increases. At a gamma of 100, the forward cone of visible light narrows to a few degrees of arc. At a gamma of 1000, it narrows to a fraction of a degree. The traveller is not watching the universe go by. She is staring down a tunnel of compressed radiation while the rest of the cosmos disappears. This is why approaching light speed is not merely an engineering challenge measured in fuel and thrust. It is a transformation in the relationship between the traveller and the rest of the universe. At ordinary speeds, A journey takes the same amount of time for the traveler and the people waiting at home. At relativistic speeds, those two durations diverge. At speeds very close to the limit, the divergence becomes so extreme that the traveler effectively leaves her own epoch. The speed of light is not just a cap on how fast you can move through space. It is a boundary beyond which the concept of a shared present, a common now between the traveler and the rest of the cosmos, ceases to function. Every particle physics experiment ever conducted confirms this structure. When protons circulate in the Large Hadron Collider at a gamma of 7,000, their internal processes run 7,000 times slower than identical processes in the laboratory. Unstable particles that would decay in microseconds at rest survive for milliseconds in the beam because their internal clocks are nearly frozen from the laboratory's perspective. This is not a side effect of high energy. It is the primary consequence. The energy did not make the particles faster in any meaningful sense. It pushed them deeper into a regime where their experience of time diverges ever more radically from the experience of the world around them. Consider the sequence of what happens as you add energy to a proton starting from rest. At low energies, the proton accelerates normally. Speed increases in proportion to energy. This is the Newtonian regime, and it works beautifully for everyday objects. At moderate energies, speed still increases, but less efficiently. The curve begins to bend. You notice that each additional unit of energy buys slightly less speed than the last. At high energies, the curve bends sharply. Speed barely changes. Almost all the added energy goes into increasing the proton's momentum and kinetic energy without producing appreciable velocity gain. At extreme energies, the proton's speed is so close to light speed that it is functionally constant. Energy doubles, then quadruples, then increases tenfold, and the speed changes in the 15th decimal place. The proton is not getting faster. It is getting, in a very real physical sense, more massive in its resistance to further acceleration. This progression reveals something that language tends to obscure. We call these machines accelerators, but what they really do at high energies is not acceleration in the intuitive sense. They are energy concentrators. They pack more and more energy into a particle that is already traveling at effectively the maximum speed. The Large Hadron Collider does not make protons go faster than the Tevatron did, not in any way a speedometer would register. It makes them carry more energy at virtually the same speed. This energy is what produces the exotic particles and violent collisions that physicists study. The speed is incidental. The energy is everything. This distinction between speed and energy is the conceptual key to understanding why the light-speed boundary is not a speed limit in the ordinary sense. A speed limit implies that you are doing something normal, moving, and there is simply a rule that says you cannot do it beyond a certain rate. The light-speed boundary is different. As you approach it, the very activity you think you are performing, accelerating, stops working the way you expect. The energy goes somewhere, but that somewhere is not increased velocity. It is increased inertia, increased relativistic mass, increased resistance to the very force you are applying. The boundary does not say stop. It says the thing you are trying to do is no longer the thing you are actually doing. And this transformation does not happen suddenly at some threshold. It happens gradually, continuously, beginning at the first instant you start moving and intensifying, without limit as you approach the boundary. There is no clean dividing line between the Newtonian regime and the relativistic regime. The transition is smooth. At walking speed, relativistic effects exist but are immeasurably small. At highway speed, they are present but negligible. At orbital speed, they become detectable with sufficiently sensitive instruments. At a significant fraction of light speed, they dominate. The universe does not wait until you are close to the limit to start changing the rules. It starts changing them immediately. You just do not notice until the changes become large enough to measure. This brings us to the threshold of the most disturbing part of the story. Everything described so far, every experiment, every measurement, every calculation, occurs in the regime below light speed. The energy asymptote, the time dilation, the inertia growth, all of these are features of the approach. They describe what happens as massive objects move faster and faster through space-time while remaining firmly below the boundary. The physics is strange but self-consistent. Every measurement still returns a real number. Every clock still advances. Every distance remains positive. No matter how extreme the distortion becomes, the framework holds together as long as you stay below the boundary. Reality bends but does not break. But what happens if you imagine, purely hypothetically, actually crossing the boundary? Not approaching it, not asymptotically curving toward it, crossing it, moving from a velocity below light speed to a velocity above it. This is where the story changes completely. Because everything the universe does as you approach the limit, the rising energy, the slowing time, the growing inertia, all of it exists to prevent that crossing. And the reason is not that the universe is enforcing some arbitrary rule. The reason is that what lies on the other side of the boundary does not look like faster travel at all. It looks like something far more disturbing, something that threatens the most basic assumption you hold about reality, the idea that causes come before their effects. What comes next will show you why crossing the light speed boundary would not just break a speed record, but fracture the ordering of events that makes the universe intelligible. Everything you have learned so far describes the approach. The rising energy, the warping of time, the asymptotic wall that prevents any massive object from reaching the speed of light through continuous acceleration. All of it is strange, but all of it is consistent. Clocks may tick at different rates, distances may contract, energy may climb toward absurd magnitudes, but through all of it, one thing remains intact: the order of events. Cause comes before effect. The match is struck before the fire starts. The ball is thrown before it hits the wall. The signal is sent before it arrives. You take this ordering for granted. You have never once in your life experienced an effect before its cause. No human being ever has. And the reason is that you, and everything you have ever interacted with, exists below the speed of light, where the causal structure of the universe holds. What happens beyond the speed of light is not a continuation of the approach. It is a rupture. The rules that govern time ordering, the sequence that keeps your reality intelligible, begin to fail. And the failure is not vague or philosophical. It is mathematically precise, experimentally motivated, and deeply disturbing. To see it clearly, we need to start with a feature of special relativity that most people have heard of, but very few genuinely understand. The relativity of simultaneity. Consider two events: a flash of light at location A and a flash of light at location B, separated by some distance. An observer standing exactly midway between A and B sees both flashes arrive at the same time and concludes the events were simultaneous. They happened at the same moment. Now consider a second observer moving rapidly from A toward B. Light from B reaches her sooner because she's closing the distance to B while moving away from A. She concludes that the flash at B happened first. A third observer, moving in the opposite direction from B toward A, concludes the reverse. The flash at A happened first. All three observers are correct within their own reference frames. There is no mistake. There is no illusion. Simultaneity, the idea that two events happen at the same moment, is not a universal fact. It depends on who is measuring and how they are moving. To make this concrete, imagine a specific scenario. A spacecraft 100 light seconds long drifts through space. At the exact midpoint of the ship, a lamp flashes. The light spreads in both directions at the speed of light. An astronaut floating at the center of the ship sees the light reach the front wall and the back wall at the same instant. Both walls are equidistant from the lamp. Both light pulses travel at the same speed. Both arrive simultaneously. She records two events. Light hits front wall, light hits back wall. In her frame, these events are simultaneous. Now, consider an observer on a nearby space station watching the spacecraft glide past at high speed. From this observer's perspective, the ship is moving forward. After the lamp flashes, the light spreading toward the front wall must chase a wall that is moving away from it. The light heading toward the back wall meets a wall that is moving toward it. Both pulses still travel at the speed of light relative to the station observer. That is the rule. The speed of light does not change, but the distances do. The backward-moving pulse has less distance to cover because the back wall is approaching. The forward-moving pulse has more distance to cover because the front wall is receding. Result: the station observer sees the light hit the back wall first and the front wall second. These are not different opinions about the same fact. These are different facts. The astronaut records simultaneous events. The station observer records sequential events. Both are correct. Neither is mistaken. Neither is experiencing an illusion caused by signal delay or light travel time. The disagreement is built into the structure of space-time. There is no master clock, no universal referee, no God's eye view that can settle which account is the true one. Both are true. Simultaneity is relative. At sublight speeds, this relativity of simultaneity is strange but harmless. Observers disagree about the timing of distant events, but they never disagree about which events caused which other events. The astronaut and the station observer might record different timestamps, but if the lamp flash caused a sensor to trigger at the front wall, both observers agree that the flash came first and the sensor trigger came second. Causality survives intact because the cause and its effect are connected by a signal, the light pulse, that travels at or below the speed of light. Their space-time separation is time-like, and time-like ordering is preserved in every reference frame. The catastrophe arrives only when signals exceed light speed, because then the events connected by that signal have a space-like separation, and space-like separations do not preserve ordering. The same disagreement about simultaneity that was harmless for the lamp and the walls becomes lethal for cause and effect. Different observers will disagree not just about when the signal arrived, but about whether it arrived before or after it was sent. The relativity of simultaneity, which at sublight speeds is a fascinating curiosity, becomes at superluminal speeds a weapon aimed directly at the logical structure of the universe. Now imagine a signal that travels faster than light, not approaching light speed, exceeding it. Moving from point A to point B in less time than light would take. In the framework of special relativity, this signal has a space-like separation from its source. Space-like intervals are the opposite of time-like intervals. They connect events that cannot be linked by any signal traveling at or below light speed, and here is the critical difference. The ordering of space-like separated events is not preserved under Lorentz transformations. Different observers, moving at different velocities, will disagree about which event happened first. Some will see the signal arrive after it was sent. Others will see it arrive at the same time. And some, moving at the right velocity, will see it arrive before it was sent. Hear that last sentence again. If a faster-than-light signal exists, there are valid reference frames in which the signal arrives at its destination before it leaves its source. The effect precedes the cause. This is not a paradox created by confused observers or sloppy measurements. It is a direct mathematical consequence of the Lorentz transformations applied to space-like connections. The same transformations that correctly predict time dilation, length contraction, and every other confirmed relativistic effect also predict, with the same rigor, that faster-than-light signals break causal ordering. The mechanism is sometimes called the tachyonic anti-telephone, a name introduced by physicists Tolman and later elaborated by Benford, Book, and Newcomb. Here is how it works. Imagine two people, Alice and Bob, stationary relative to each other. Alice sends Bob a faster-than-light message. In Alice's reference frame, the message travels forward in time, from her present to Bob's near future. Bob receives it, then replies with his own faster-than-light message. In Bob's frame, his reply also travels forward in time. But here is the problem. Because Alice and Bob are in different reference frames for the two transmissions, and because faster-than-light signals connect space-like separated events, the chain of two messages can form a closed loop. Bob's reply arrives at Alice's location before she sent the original message. Alice receives a reply to a message she has not written yet. This is not an edge case. It is not a contrived scenario that requires impossibly precise velocities. Any pair of faster-than-light signals exchanged between two observers in relative motion can in principle produce this effect. The speed of the signal, the velocity of the observers, and the direction of transmission determine whether the loop closes, but the possibility exists for any superluminal exchange. The faster the signal exceeds light speed, the wider the range of observer velocities that experience reversed causality. Faster-than-light communication is not just fast mail, it is a time machine. This is where tachyons enter the story. Tachyons are hypothetical particles first proposed by physicist Gerald Feinberg in 1967. The The concept arises from a curious mathematical property of the Lorentz equations. For particles with positive real mass, the equations describe objects that always travel below light speed. For massless particles like photons, the equations describe objects that always travel at exactly light speed. But there is a third mathematical possibility. Particles with imaginary mass, where the mass squared is a negative number, yield solutions that always travel above light speed. These are tachyons. Tachyons, if they existed, would be strange objects. They could never slow down to light speed, just as ordinary matter can never speed up to it. The light speed barrier would work in reverse for them. Adding energy to a tachyon would slow it down, and removing energy would speed it up. A tachyon with zero energy would travel at infinite speed. These properties are mathematically consistent within the narrow framework of the energy-momentum equations, but they carry enormous conceptual problems. The first problem is the causality violation just described. If tachyons can carry information, they enable the construction of antitelephones and closed causal loops. This alone is enough for most physicists to regard tachyons as strong evidence that faster-than-light particles are forbidden by the deeper structure of physics, not just difficult to create. The equations permit them in a limited mathematical sense, but the physical consequences are so destructive to causal order that the permission is widely interpreted as revealing a boundary the universe does not allow crossing. The second problem is observational. No tachyon has ever been detected. Not in particle accelerators, not in cosmic ray observations, not in any astrophysical dataset. Every experiment designed to find evidence of faster-than-light particles has returned a null result. In 2025, a team at Tufts University published a study that placed direct observational upper bounds on tachyon mass using black hole physics. Their argument was elegant. If tachyons exist, black holes should emit them through Hawking radiation, and the emission rate would be dramatically enhanced for heavy tachyons. A sufficiently massive tachyon species would cause black holes to evaporate far faster than observed. The existence of stable, long-lived black holes of a few solar masses observed to persist for billions of years, therefore rules out tachyons above certain mass thresholds. The paper concluded that the observation of ordinary stellar mass black holes constitutes direct evidence against tachyons associated with unification energy scales or quantum gravity. Tachyons are not just undetected. The universe appears to be structured in a way that excludes them. The physics community experienced one dramatic episode that illustrates just how seriously the light speed boundary is taken, not as an engineering obstacle, but as a structural principle whose violation would signal a crisis in fundamental physics. In September of 2011, a collaboration called OPERA announced results from an experiment measuring the travel time of neutrinos sent from CERN in Geneva to the Gran Sasso laboratory in central Italy, a distance of roughly 730 kilometers through the Earth's crust. The neutrinos appeared to arrive approximately 60 nanoseconds earlier than light would have, suggesting they had traveled faster than the speed of light. The response from the global physics community was not excitement, it was alarm. 60 nanoseconds faster than light, if real, would not be a thrilling breakthrough. It would be a catastrophe for the logical consistency of modern physics. Every consequence we have discussed, the causality violation, the closed causal loops, the dissolution of time ordering, would follow directly from confirmed superluminal particle travel. Physicists did not celebrate the result. They immediately assumed something was wrong with the measurement. Hundreds of papers appeared within weeks, most of them analyzing what the result would imply if it were correct, and finding the implications unacceptable. Some proposed exotic theoretical frameworks that might accommodate superluminal neutrinos without destroying causality, but these frameworks required abandoning or radically modifying principles that had been confirmed by decades of independent experiments. The overwhelming professional consensus was that the measurement had to contain an error because the alternative was the collapse of the causal framework that makes physics coherent. They were right. By February of 2012, the OPERA collaboration announced that it had identified two equipment problems. One was a fiber optic cable connecting a GPS receiver to an electronic card, which had not been fully screwed in, introducing a timing error. The other was a clock oscillator that had been ticking slightly too fast. When both errors were corrected, the neutrino arrival times matched the speed of light within experimental uncertainty. The superluminal signal vanished. Physics exhaled. But the episode revealed something important about how the scientific community understands the light speed boundary. The reaction was not proportional to 60 nanoseconds. It was proportional to what 60 nanoseconds would mean. Physicists were not worried about a small timing error. They were worried about the entire edifice of causal physics. The fact that thousands of researchers across the world converged almost instantly on the conclusion that the measurement must be wrong before the error was found speaks to how deep the conviction runs. The speed of light is not treated as a record that might someday be broken. It is treated as a condition for the internal consistency of physical law. Violating it would not add a new chapter to physics. It would invalidate the book. The Grand Sarceau episode is the closest the scientific world has come to a confirmed violation of the light speed boundary. It lasted 5 months before collapsing under scrutiny. And in those 5 months, the physics community behaved exactly as you would expect from people who understood that what was at stake was not a speed record but the ordering of reality itself. The third problem is quantum field theory. In modern particle physics, tachyonic fields are not interpreted as fields that produce faster-than-light particles. They are interpreted as indicators of vacuum instability. A tachyonic mass term in a quantum field theory signals that the vacuum state the field occupies is not the lowest energy configuration. The field will roll downhill to a new vacuum where the tachyonic term disappears and all particles behave normally. This process, called tachyon condensation, is well understood and plays a role in the Higgs mechanism and in string theory. The tachyon in these frameworks is not a particle zooming through space faster than light. It is a mathematical signal that the theory needs to be reorganized around a different ground state. Once that reorganization is complete, no faster-than-light particles remain. So tachyons as physical, detectable, faster-than-light objects remain firmly hypothetical, unsupported by any confirmed observation, constrained by black hole physics, and reinterpreted in quantum field theory as something other than superluminal particles. Yet the causality problems they illustrate are not hypothetical. They are structural features of any faster-than-light scenario within special relativity. Tachyons simply make the problem most visible. Any mechanism that transmits information faster than light, whether through exotic particles, wormholes, or engineered space-time geometries, runs into the same causal catastrophe. This leads to the question people have been asking since Einstein. Can you get around the problem? Can you build a faster-than-light system that avoids causality violation? The most famous attempt is the Alcubierre warp drive, proposed by Mexican physicist Alcubierre in 1994. The idea is ingenious. Instead of moving a spacecraft through space-time faster than light, you reshape space-time itself around the ship. Space contracts ahead of the vessel and expands behind it, creating a wave in the fabric of space-time that carries the ship forward. Inside the bubble, the ship is locally at rest. It is not violating special relativity within its own patch of space-time. The superluminal motion is achieved by the geometry of space itself, not by the ship's movement through space. This sounds like it might dodge the causality problem. The ship is not moving faster than light locally. Space-time is doing the work, but the escape is illusory. Multiple independent analyses have shown that if an Alcubierre warp bubble can exceed the speed of light, it can be used to construct closed time-like curves. The argument follows the same logic as the tachyonic antitelephone. Two warp bubbles, moving in opposite directions between two observers in relative motion, can form a causal loop in which signals arrive before they are sent. The geometry of the bubble does not protect you. As long as the net effect is superluminal travel from one location to another in some reference frame, the Lorentz transformations guarantee that other reference frames will see reversed causality. And the Alcubierre drive carries additional problems that make it even less viable than the tachyon concept. The space-time geometry it requires demands a specific energy configuration that violates what physicists call the weak energy condition. Ordinary matter and energy always produce positive energy density. The warp bubble requires regions of negative energy density, a substance that has never been observed in the quantities needed and may not exist at macroscopic scales. Quantum field theory allows tiny, fleeting violations of energy conditions in phenomena like the Casimir effect, but these are submicroscopic and transient. The warp drive requires sustained, large-scale, precisely configured negative energy that no known physics can supply. Furthermore, The bubble creates a horizon problem. Once the warp bubble is moving faster than light, the interior of the bubble becomes causally disconnected from the front wall. Light signals from the ship cannot reach the leading edge of the bubble because the edge is receding faster than light relative to the interior. This means the occupant of the ship cannot control, steer, or stop the bubble from inside. The pilot is a passenger. The destination cannot be changed in flight. And creating the bubble in the first place requires manipulating spacetime ahead of the ship, in a region the ship has not yet reached, raising the question of how you start the process at all. Recent work has continued to expose these difficulties. In early 2026, researchers Santos Pereira, Abreu, and Hibeiru published a study in the European physical journal C, exploring how to mathematically match the Alcubierre spacetime with the flat Minkowski spacetime of the surrounding universe. Their work advanced the theoretical formalism but did not resolve the fundamental energy condition problem. In the same period, physicist Na-Ta Ryo, whose own research helped clarify warp drive limitations, stated publicly that superluminal travel is impossible and identified steering and stopping as unsolved and potentially unsolvable problems. And just this year, researchers Buchert and Fratzkowiak published a paper reporting what they described as an expected generic instability of the warp field. In a specific example they studied, the warp bubble, even if it could be created, may not be stable enough to sustain. The Alcubierre drive is not a blueprint. It is a thought experiment that reveals how deeply the causality problem is embedded in any superluminal scheme. Even the most creative attempt to circumvent the light-speed boundary, using the permissiveness of general relativity's geometry, runs headlong into the same wall. Negative energy that does not exist, causal loops that destroy chronology, horizons that prevent control, instabilities that threaten collapse. The universe does not offer a clever workaround. Every path to faster-than-light motion leads to the same destination: the unraveling of cause and effect. General relativity itself contains solutions that feature closed time-like curves, paths through spacetime that loop back and allow an object to return to its own past. Kurt Gödel discovered the first such solution in 1949. His rotating universe model, a mathematically valid solution to Einstein's field equations, contained curves along which a traveller could, in principle, revisit events in her own history. Other solutions followed: rotating black holes, certain configurations of cosmic strings, traversable wormholes, all contain closed time-like curves under specific conditions. The mathematics of general relativity does not automatically forbid time loops. It permits them in geometries that are internally consistent solutions of the field equations. This permissiveness troubled physicists enough that Stephen Hawking proposed what he called the chronology protection conjecture in 1992. The conjecture states that the laws of physics do not allow the creation of closed time-like curves in any physically realistic scenario. Hawking argued that quantum effects would destabilize any spacetime geometry approaching the formation of a closed time-like curve. Energy densities would spike to infinity at the chronology horizon, the boundary in spacetime where closed time-like curves first appear, destroying the geometry before the loop could close. The universe, Hawking suggested, protects chronology from violation. The chronology protection conjecture is widely believed, but not proven. It remains a conjecture, not a theorem. No one has demonstrated from first principles that the laws of physics absolutely prevent closed time-like curves in all cases. The arguments in its favour rely on semi-classical calculations that combine quantum field theory with classical general relativity, an approximation that breaks down precisely at the energy scales where the conjecture matters most. A full theory of quantum gravity might confirm chronology protection, or it might reveal loopholes. We do not know. What we do know is that every proposed mechanism for creating closed time-like curves requires conditions that appear to be physically unrealizable. Exotic matter, with negative energy density, infinite rotating cylinders, cosmic strings, with precise configurations that have never been observed, wormholes held open by substances that may not exist. The universe tolerates these solutions in pure mathematics but appears to block every physical path to constructing them. This pattern, is itself significant. Wherever physicists look for a route past the light-speed boundary, they find the same structure. The mathematics technically allows solutions that violate causal ordering, but the physical conditions required to realize those solutions are always absent, forbidden, or unstable. It is as if the universe maintains a firewall between mathematical possibility and physical reality, specifically at the point where causality would fail. The speed of light is not just the speed at which light travels. It is the speed at which the causal firewall is set. Everything at or below this speed preserves the ordering of cause and effect. Everything above it threatens to destroy that ordering. And every mechanism that might breach the wall turns out, upon closer inspection, to require ingredients the universe does not supply. This should reframe how you think about the light-speed boundary entirely. It is not a speed limit in the way that a highway speed limit is a speed limit. A highway speed limit is an arbitrary number chosen by regulators. You can exceed it if you are willing to accept the consequences. The light-speed boundary is not arbitrary. It is structural. Exceeding it does not merely incur a penalty. It dissolves the logical framework that makes penalties, causes, effects, sequences, and events meaningful in the first place. Consider the implications if causality actually broke down. If effects could precede causes, then the concept of a decision becomes incoherent. You act because of a reason. The reason precedes the action. If the action can precede the reason, the relationship between intention and outcome collapses. Physical law becomes uncomputable. If the result of an experiment can influence its initial conditions, then no experiment has a definitive outcome. Every measurement becomes contingent on future events that have not yet occurred. The feedback loops would be infinite. The grandfather paradox, in which a time traveler prevents her own birth, is merely the most dramatic illustration. The deeper problem is that every causal chain becomes vulnerable to retroactive disruption. Prediction becomes impossible. History becomes mutable. The arrow of time, which gives the universe its narrative direction, its sense of before and after, dissolves. None of this is speculative exaggeration. These are the direct mathematical consequences of superluminal signal transmission within the framework of special relativity. And special relativity is not a speculative framework. It is one of the most rigorously confirmed theories in the history of science. Its predictions have been verified to precisions exceeding 1 part in 10 billion. The 2026 gamma-ray study tightened constraints on Lorentz invariance violation to levels that would have been unimaginable a generation ago. The framework stands, and within that framework, faster-than-light motion and intact causality are mutually exclusive. You can have one or the other, not both. This mutual exclusivity is the real content of the light speed limit. It is not about velocity. It is about the preservation of logical order. The speed of light is the fastest speed at which causality can propagate, and everything the universe does near that boundary, the energy asymptote, the time dilation, the inertia growth, serves to prevent massive objects from reaching or crossing it. The boundary is not frustrating human ambition. It is protecting the coherence of the event structure that makes ambition, thought, and experience possible. But there is one phenomenon that appears to violate this entire picture. One confirmed observation in which things move apart faster than light, right now, all across the universe, without producing a single causality paradox. Understanding why this exception works, and why it does not rescue the dream of faster-than-light travel, requires looking at the one place where superluminal motion is real, measured, and completely harmless: the expansion of space itself. Right now, as you listen to this, galaxies are flying away from Earth faster than light. Not metaphorically, not in some hypothetical model. Right now, in confirmed observational reality, objects at the edge of the observable universe are receding from us at velocities exceeding 3 times the speed of light. This is measured. This is documented. This has been known for decades, and it does not violate a single law of physics. If you have followed everything up to this point, that statement should feel impossible. We have spent 3 parts establishing that the speed of light is a structural boundary that cannot be crossed, that approaching it warps time and demands infinite energy, that exceeding it would demolish causality and dissolve the ordering of events. And now the universe itself appears to be casually ignoring its own deepest rule, flinging galaxies apart at superluminal speeds without consequence. Either everything we have discussed is wrong, or there is a distinction so fundamental that it changes what the words faster than light actually mean. The distinction is real, and understanding it is the key to grasping what the light speed limit actually protects. The expansion of the universe was first inferred observationally in the 1920s. Astronomer Vesto Slipher had already measured the redshifts of distant galaxies, finding that nearly all of them were moving away from us. Edwin Hubble, building on Slipher's data and his own distance measurements, published the relationship in 1929. Galaxies farther away recede faster. Double the distance, and you roughly double the recession velocity. This proportionality, now called Hubble's law, revealed that the universe is not static, it is expanding. Every galaxy is moving away from every other galaxy, not because the galaxies are flying through space like shrapnel from an explosion, but because the space between them is growing. This distinction between moving through space and space itself growing is not a technicality. It is the entire point. When a galaxy recedes from Earth at superluminal velocity, the galaxy is not traveling through its local spacetime faster than light. Locally, in its own patch of the cosmos, the galaxy is essentially at rest. Stars orbit its center at normal speeds. Planets follow normal trajectories. Light moves at exactly the speed of light in every direction. Nothing within the galaxy violates special relativity. What is happening is that the space between us and that galaxy is stretching. New space is being created along the line connecting us. The galaxy is not moving away from us in the way a car drives away from a stoplight. It is standing still while the road between us gets longer. Hubble's law quantifies this expansion with a single number called h0, the Hubble constant. Current measurements place it at approximately 67 to 73 kilometers per second per megaparsec, depending on the measurement technique. This means that for every megaparsec of distance, roughly 3.26 million light-years, the recession velocity increases by about 70 kilometers per second. At small distances, the effect is negligible. Nearby galaxies recede at modest speeds well below light speed. But because the relationship is proportional to distance, there exists a threshold, called the Hubble distance, beyond which the cumulative expansion rate exceeds the speed of light. That threshold sits at roughly 14 billion light-years. Galaxies beyond this distance are receding from us faster than light, and there are many such galaxies. The observable universe extends to a co-moving distance of about 46.5 billion light-years in every direction. The overwhelming majority of that volume lies beyond the Hubble distance. Most of the galaxies we can observe in deep-field images are currently receding from us faster than light. How can we see them if they are moving away faster than light? Because the light we are seeing left those galaxies billions of years ago, when they were much closer and receding much more slowly. The photons began their journey in a region of space that was, at the time of emission, receding at sublight speed. During the billions of years those photons traveled, space continued expanding, carrying the source galaxy ever farther away. By the time the light reaches our telescopes, the galaxy that emitted it has crossed the Hubble distance and is now receding superluminally. We see the galaxy as it was, not as it is. The light is a fossil, an ancient record of a source that has long since disappeared beyond the reach of any future signal we might send. This is where the crucial distinction emerges. The superluminal recession of distant galaxies does not transmit information faster than light. No signal, no causal influence, no chain of cause and effect is outrunning photons. The galaxy is not sending us a message at superluminal speed. It emitted light at the normal speed of light in its local frame, and that light traveled through expanding space at the normal speed of light in every local frame it passed through. The expansion of space stretches the wavelength of the light, producing redshift, and increases the total distance the light must cross, producing longer travel times. But at no point does anything move through its local spacetime faster than light. The superluminal recession is a cumulative effect of expansion, integrated over billions of light-years, not a local violation of the speed limit. This is precisely why the expansion of space does not produce causality violations. The tachyonic anti-telephone requires sending a signal from point A to point B faster than light through spacetime. Cosmic expansion does not do this. No one at Galaxy A is communicating with Galaxy B at superluminal speed. No event at A is causing an effect at B faster than light would carry it. The expansion simply moves A and B apart, increasing the distance between them without creating any causal link between them that violates the light speed constraint. The space-time between them stretches, but no information crosses that space-time faster than photons can carry it locally. The discovery that the expansion is accelerating made this picture even more dramatic. In 1998, two independent research teams studying distant supernovae found that the universe's expansion rate is not slowing down under gravity, as nearly all cosmologists had expected, but speeding up. Something is pushing space apart with increasing vigor. This something was named dark energy, and it constitutes approximately 68% of the total energy content of the universe. The discovery earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. Dark energy's nature remains one of the deepest unsolved problems in physics. The simplest model treats it as a cosmological constant, a fixed energy density inherent to empty space itself. In this model, every cubic meter of vacuum contains a tiny amount of energy that exerts a repulsive gravitational effect. As space expands and more vacuum is created, the total dark energy increases, driving further expansion. The process feeds itself. More space means more dark energy, means faster expansion, means more space. The acceleration is exponential in the long run. The consequences for the far future are extraordinary and grim. As expansion accelerates, galaxies beyond our local gravitationally bound group will recede faster and faster. Their light will be redshifted to longer and longer wavelengths, growing dimmer and dimmer until it drops below any conceivable detection threshold. Within roughly 100 billion years, every galaxy outside our local group will have crossed beyond the observable horizon permanently. Future astronomers, living in the merged remnant of the Milky Way and Andromeda, will look out at a sky containing only their own galaxy. The rest of the universe will have vanished, not destroyed, simply carried beyond the reach of light forever. This vanishing act illustrates the same principle we have been exploring throughout this entire story, but from the opposite direction. When a galaxy crosses the cosmological horizon, it does not break the speed of light locally. It simply recedes at a cumulative rate due to expansion that exceeds the speed at which light can bridge the growing gap. Light from that galaxy, emitted after the crossing, will never reach us. Not because the light is slow, but because the space the light must cross grows faster than the light can traverse it. The galaxy is not gone, it still exists. Stars still burn, planets still orbit, but it is causally disconnected from us. No signal, no force, no influence of any kind can ever pass between us again. The expansion of space has severed the causal link permanently. The permanence of this disconnection deserves emphasis, because it reveals the light speed limit operating at its most absolute. When a galaxy crosses the cosmological horizon, the severing is not temporary. It is not a matter of waiting long enough for a signal to bridge the gap. The gap is growing faster than any signal can cross it. Light emitted from that galaxy after the crossing will travel through space at the full speed of light in every local frame it passes through, but the space ahead of it is expanding faster than the light can eat through it. The photon makes progress locally but falls behind globally. It is like running on a treadmill that accelerates faster than you can sprint. You are moving, genuinely moving, but the finish line recedes faster than you approach it. That photon will travel forever without reaching us. It will never arrive. Not in 1 billion years. Not in 1 trillion. Not ever. This means the observable universe is fragmenting into causally isolated islands. Our local group of galaxies, gravitationally bound and therefore resistant to expansion, will remain a single connected region. We will be able to send signals, exchange light, and maintain causal contact with Andromeda, with the Magellanic Clouds, with the few dozen galaxies held together by our shared gravitational well. But everything beyond that local island is sliding away. Other galaxy groups and clusters, each one its own gravitationally bound island, are being carried beyond our reach by the same expansion that created the distance between us in the first place. Each island will eventually become a self-contained causal universe, Events within the island influence each other normally. Light travels between member galaxies, gravity binds the structure together. Physics works, causality holds. But no event on one island will ever again influence an event on any other. No gravitational wave, no photon, no neutrino will cross the expanding gulf between isolated groups. Each island becomes a universe unto itself, not because the others have been destroyed, but because the speed of light cannot keep up with the rate at which space is being created between them. This cosmic fragmentation is not a distant theoretical possibility. It is already underway. Galaxies at the edge of our observable universe are already beyond causal reach. Signals we send today will never arrive at the most distant objects we can currently photograph. The photographs themselves are relics, images of galaxies that have long since crossed our causal horizon. We see their past. We can never touch their future. The speed of light drew a circle around us, and the expansion of space is slowly, permanently, erasing everything outside that circle from our causal reality. What remains inside the circle is governed entirely by the same rules we have explored throughout this story. Causes precede effects. Light travels at a finite, constant speed. Time moves forward. Events form sequences. Physics is computable. Reality is coherent. The light speed limit, the same constraint that prevents protons from reaching the boundary, that warps time for relativistic travelers, that forbids tachyons and collapses warp drives, is the same constraint that defines the edges of our causal island and determines which parts of the cosmos will remain part of our story and which will fade permanently into silence. The speed of light is not merely a local rule about how fast things can move. It is the architectural principle that determines the shape, the reach, and ultimately the boundaries of every causally connected region in the universe. And this is the deepest insight the expansion offers about the light speed limit. Causal disconnection through expansion is not a violation of the limit. It is the limit in action. The speed of light defines the maximum rate at which causal influence can propagate through local spacetime. Expansion can separate regions of the universe faster than this rate, but in doing so, it does not create superluminal causation. It creates causal isolation. The regions simply stop being able to affect each other. The light speed limit is not preventing the universe from expanding. It is determining which parts of the expanding universe can still talk to each other. This reframes the entire meaning of the light speed boundary. It is not a restriction on motion. It is a definition of causal reach. It tells you the maximum distance in space-time over which one event can influence another. Anything within your light cone, the expanding sphere of space-time that your signals can reach, is causally accessible. Anything outside it is not. The boundary of your light cone moves outward at the speed of light. Nothing you do can extend it faster. The expansion of space can shrink it by pulling regions beyond its edge, but nothing can push the edge outward faster than light carries it. Every argument for why faster-than-light travel is impossible, the energy asymptote, the time dilation, the inertia growth, converges on this single truth. These are not separate obstacles. They are different faces of the same geometric reality. Spacetime has a structure. That structure includes a maximum propagation speed for causal influence. Every phenomenon we have examined, from GPS clock corrections to proton beams to tachyon exclusions to warp drive instabilities, is a consequence of this structure. The speed of light is not a speed. It is the causal grain of the universe, the rate at which reality can update itself from one event to the next. Now consider what it would mean for this grain to be absent. Imagine a universe with no maximum speed for causal propagation. In such a universe, signals could travel from any event to any other event instantaneously or faster. Every event in the cosmos would be causally accessible to every other event. The concept of distance would lose its causal meaning. There would be no light cones, no causal horizons, no separation between regions that can influence each other and regions that cannot. Every point in the universe could, in principle, affect every other point with no delay. At first glance, this might sound liberating. No speed limit, no isolation, no unbridgeable gulfs between stars. But the consequences would be catastrophic. Without a finite propagation speed for causality, there would be no stable ordering of events. Time ordering depends on causal structure. Before, and after are defined by which events can influence which. If everything can influence everything instantaneously, then the directionality of time becomes undefined. Cause and effect becomes circular. The arrow of time, which in our universe points from past to future along the direction of increasing entropy, would have no anchor. Events would not form sequences. They would form loops, tangles, contradictions. Physics itself would become impossible. Physical laws are differential equations that evolve a system's state forward in time. If time has no consistent direction, these equations cannot be solved. Initial conditions would not determine future states, because future states could retroactively alter initial conditions. Prediction, the core activity of all science, requires that causes precede effects. Without that ordering, there is no prediction. There is no science. There is no coherent experience of any kind. This is not a hypothetical horror story. This is the precise mathematical consequence of removing the light speed limit from the equations of physics. Special relativity with a finite speed of light produces a universe where time has a consistent direction, where causality is preserved, and where events form a coherent history. Remove the speed limit, or allow it to be exceeded, and these properties vanish. The equations that describe a well-ordered universe become the equations that describe causal chaos. The speed of light, then, is not a frustrating limitation on human ambition. It is one of the conditions that make human ambition possible. It is the boundary that keeps time pointed in one direction. It is the constraint that ensures causes produce effects rather than the reverse. It is the rule that allows events to form stories, histories, narratives with beginnings, middles, and ends. Without it, nothing would happen in any order. And without order, the concept of happening itself loses meaning. There is a tendency, when people learn about the light speed limit, to feel a kind of existential disappointment. The stars are far away, the universe is vast, and we are trapped, confined to our tiny corner of the cosmos by a law that seems designed to frustrate our deepest exploratory instincts. The speed of light feels like a prison wall, but the framing is exactly backward. The speed of light is not the wall of a prison, it is the foundation of a building. Remove it and the building does not open up. It collapses. You are not trapped by the light speed limit, you exist because of it. Every thought you have ever had depends on electrochemical signals traveling through neurons at speeds far below the speed of light. Those signals arrive in a specific order. They produce a specific sequence of experiences. That sequence is your consciousness. If those signals could arrive in any order, or before they were sent, your thoughts would not become faster. They would become incoherent. Consciousness requires temporal ordering, and temporal ordering requires a finite maximum speed for causal propagation. You are a creature of the light speed limit in the most literal sense. Your ability to think, to perceive, to experience a moment followed by the next moment is underwritten by the same constraint that prevents you from reaching Alpha Centauri in an afternoon. The same is true of every physical process in the observable universe. Stars burn because nuclear fusion proceeds in a specific causal sequence. Hydrogen nuclei collide, fuse, release energy, and that energy propagates outward. Each step depends on the previous one. If the sequence could be reversed or scrambled, fusion would not produce energy. It would produce nonsense. Planets orbit because gravitational influence propagates at the speed of light, creating a consistent gravitational field that changes smoothly and predictably. If gravity propagated instantaneously, orbital mechanics would become chaotic and possibly paradoxical. Chemistry, biology, geology, every science that describes processes unfolding over time depends on causal ordering. DNA replicates because molecular interactions proceed in a fixed temporal sequence. Enzymes catalyze reactions because substrates arrive at active sites in a specific order. Evolution operates because mutations occur, are tested by selection, and propagate through populations along a one-directional timeline. Reverse the arrow, scramble the sequence, and none of these processes function. Life does not merely prefer causal order, life requires it. And so we arrive at the true meaning of the title. What really happens beyond light speed is not faster travel. It is not liberation from distance. It is not humanity finally slipping the leash and reaching the stars. What really happens beyond light speed, according to the most rigorously confirmed framework in modern physics, is the dissolution of the causal structure that makes events happen in order. Beyond light speed, the distinction between before and after becomes observer-dependent to the point of incoherence. The past becomes reachable. The future becomes alterable. And the logical architecture that allows one event to cause the next, the architecture that underwrites time, experience, physics, and thought, fractures. The universe does not prohibit faster-than-light travel the way a government prohibits speeding. It prohibits it the way mathematics prohibits a square circle. The prohibition is not a rule imposed from outside. It is a consequence of the internal logic of spacetime. Within that logic, faster-than-light motion for massive objects is not merely difficult or expensive or impractical. It is structurally incoherent, a contradiction in the geometry that defines what motion, time, and causation mean. The expansion of space confirms this interpretation rather than undermining it. Space can stretch at any rate because stretching space does not create causal connections. It severs them. Galaxies carried beyond the Hubble distance do not gain the ability to influence us faster than light. They lose the ability to influence us at all. The expansion is not an exception to the light speed rule. It is the rule operating at cosmological scale, drawing the boundary between what can affect what, and letting the universe grow larger while keeping causal structure intact within every local region. We began this story with a simple, intuitive assumption. Beyond light speed is just faster, more speed, quicker arrival, a bigger number on a cosmic speedometer. That assumption is wrong in a way that goes deeper than engineering, deeper than energy budgets, deeper than the limitations of current technology. It is wrong because the speed of light is not a speed in the ordinary sense. It is a boundary condition on reality itself. It defines the maximum rate at which the universe can process cause into effect. It sets the grain size of causal structure, the smallest possible delay between an event and its consequence. And that delay, small as it is the thread that holds the entire tapestry of time together. Pull the thread, and nothing unravels gracefully. There is no regime beyond the speed of light where physics resumes in a faster key. There is no other side of the wall where travelers arrive sooner and life goes on. The mathematics of special relativity, confirmed to extraordinary precision across more than a century of increasingly sensitive experiments, describes a boundary beyond which the framework that makes physics a coherent enterprise stops functioning. Not because we lack better equations, because the concept of an equation evolving a state forward in time depends on time having a forward direction, and that direction depends on the speed of light being the limit it is. The deepest shock of this story is not that we cannot go faster than light, it is that we would not want to. Not because the destinations are not worth reaching, but because reaching them superluminally would mean arriving in a universe where arrival and departure have lost their meaning, where the signal you send can arrive before you decide to send it, where effect and cause trade places depending on who is watching, where the history of the cosmos becomes a document anyone can edit from any page. The speed of light is not the universe saying no, it is the universe holding itself together. It is the condition that keeps before pointed one way and after pointed the other. It is the reason your memories are of the past and your plans are for the future and not the reverse. It is the reason physics works, chemistry works, biology works, thought works. It is the reason anything works at all. And perhaps the most humbling realization is this. The same boundary that confines us to our small corner of the cosmos is the boundary that makes corners and cosmos and us possible. The speed of light does not limit what we can do. It preserves the very framework in which doing and being and knowing have meaning. We live in a universe where events happen in order, where causes produce effects, where time moves forward and stories have endings. That universe exists because of the speed of light, not in spite of it. We are not prisoners of this limit. We are its beneficiaries, and every photon crossing the void between stars, every signal arriving precisely after it was sent, every clock ticking faithfully forward, is evidence that the speed of light is doing the one thing it was always meant to do, holding reality together.